Hey everybody, thanks for coming to the seminar. Happy Halloween. Today I'm so excited to host Andy Cross, who is just reconstructing his geographical path. So he did his bachelor's degree at the University of Liverpool. He then went on to New Zealand to the University of Otago to do his PhD. Then he visited Brown University. He was postdocing at WashU St. Louis, which is about where we met. Yeah. Then he went to University of Pennsylvania, and right now he is an assistant scientist at Hui, which is Cape Town.
Yes.
I came across some of his work back when I was working on the theory side of rock deformation, and he was running all the super cool experiments at pretty exotic conditions to kind of deform the rocks and learn about really the microscopic physics of what makes solids strong or weak, how they interact with different mineral phases and contrast, and really kind of breaking up to target the complexity of real Earth rocks, and it's only humbling to the theoreticians about who are kind of working with more idealized models. Since then, as I've been following in this work, he's expanded to also look at, both other minerals, but also ice, and looking both for Earth conditions and even other planets like Mars. Thank you so much for coming to visit us. Very excited about your talk. Take care away.
All right, thanks for that great introduction. Yeah, I'm really glad we could make this work. I actually happen to be in Chicago this week performing. I'm over at Argonne National Lab performing experiments at the Advanced Photon Synchrotron, Advanced Photon Source Synchrotron. So just it worked out really nicely that I could actually come and give a talk about all these experiments that we've been doing. So yeah, the broad kind of theme of the talk is how do phase transformations impact the rheology, the strength and flow of Earth-forming minerals. And before I start, I'd be remiss if I didn't just point out that this is a big collaborative effort with a bunch of really great collaborators. We've got a team of, there are 8 of us at APS right now running kind of 16, 18-hour shifts around the clock to try and churn out as many experiments as we possibly can this week. All right, so why do we care about phase transformations in the first place? And really, since the emergence of plate tectonic theory about 60, 70 years ago, we've come to really appreciate the fact that the interior of the Earth is a super dynamic place, right? So we've got material being buried in mountain belts and oceanic crust being shoved down into the mantle, possibly all the way down to the core mantle boundary. We've got material rising up from the core mantle boundary in mantle plumes. And then, of course, we've also got this constant kind of churning of the mantle during mantle convection. And so kind of the task of rock squeezers like me is to figure out how the rocks that make up Earth flow and deform over geologic timescales. So typical experiments look a little bit something like this. A lot of the attention has been focused to date on single mineral systems. So just taking these are some of Phil Skenner's postdoc experiments of Brown, taking aggregates of, in this case, a coarse grained dunite, and then squeezing and twisting them in a gas medium rig to high shear strains, and looking at things like grain size reduction, the way that crystal lattices will rotate in a line, and then also measuring some mechanical data. So on the right here, we've got shear stress as a function of shear strain, so the amount of deformation. And so these experiments are relatively straightforward. You just load up at some constant rate, and you have this linear elastic portion, small strains. Then that reaches some yield stress, start to turn over, and so you get towards a steady state stress at that given rate. Step the rate up, measure another steady state stress, and once more and once more. And so that relationship between shear stress and strain rate gives you some indication about how to best extrapolate the experiments from timescales of days, maybe even weeks, to millions of years. And yeah, like I say, most of our attention as a community so far has been focused on single phase systems. We have, particularly in the past 10 years, started moving more towards thinking about how phases interact during deformation, so how they intermix, and what that means for bulk scale rheology. And Elvira's done a lot of the really tricky theory behind this. We just squeeze stuff in the lab, but Elvira's actually put in the hard work of figuring out what this actually means from a physical perspective. So on the left here are some experiments I did during a postdoc in St. Louis, taking out two-phase aggregates of calcite and anhydrite and then just twisting them to progressively higher strains, taking them out and having a look at what's going on. And so you get, it's kind of hard to see on these backscatter images, but you do get progressive grain size reduction, and associated with that is an order of magnitude or 2 orders of magnitude weakening with increasing deformation. And similarly, experiments have been done on olivine OPX aggregates in David Kolsted's lab at Minnesota by Microstructural. But so that's just taking two-phase aggregates, and but we know that mineral assemblages are not constant through time, particularly with all this burial and exhumation that goes on in Earth. And we know that as we move through pressure, temperature, space, minerals will undergo phase changes, phase transformations, metamorphic reactions. And so here are just some examples for continental crust and for the mantle as a function of pressure and temperature. So there are a whole myriad of phase transformations that are happening within Earth's interior. And so the question really is, well, how do these impact our rheological properties? And compared to the experiments on single-phase aggregates and two-phase aggregates, there really haven't been too many experiments that have looked into this, relatively speaking, although interest does go back about almost 100 years. These are some really wonderful experiments done by Albert Sauveur back in the early 1920s, taking bars of iron and twisting them at a constant rate in a horizontal tube furnace. So the center of the bar is hot, and then it gets colder as you get out towards the edges. And so if we just look at this top experiment, each one of these is a separate experiment. We look at this top one. This was performed at a temperature of 600 degrees in the center of the bar, and then the edges are colder. And so we see that as you increase temperature, strain gets localized, deformation localizes into the hottest, weakest part of the bar. That makes sense. As we go to higher and higher temperatures, again, we still see the same thing. Deformation is localized in the middle of the bar. There's more there. But we also have these two shear zones, two localized shear zones that are equidistant from the hotspot. And it turns out that the locations of these localized shear zones correspond to the alpha to gamma ion transition. So the phase transformation here is having a big effect on the strength of these bars just locally. Let's look at a different system. This is some experiments done across the ice 1-2 phase boundary, where these are pretty neat as well. So they took a sample of ice, put it in a soft indium jacket with some sort of spacer, and then a spring that had been calibrated to apply some differential stress on the order of 0 to, well, they did experiments without the spring at 0 MPa differential stress, and then up to about 3 MPa using a spring load geometry. Put this whole thing into a gas rig, basically a big pressure cooker, and then increase the confining pressure to take the sample from the ice 1 phase, that's regular ice that we're all familiar with, and then take it into the higher pressure ice 2 field. And they pull the samples out afterwards and then measure the amount of plastic deformation, so the amount of shortening of the sample. And as you increase the amount of applied stress, the strain in the sample increases as well, even though it's just gone from ice 1 to ice 2 and then back under a relatively small differential stress. You're getting quite a large shortening of the sample, up to about 20%. And so experiments like these fed into, there's a really seminal paper by Greenwood and Johnson from 1965, just kind of describing this phenomenon of what's referred to as transformation plasticity or transformation superplasticity. And so the model goes that if we just take a look at some sort of standard creep curve, right? So we've got our linear elastic portion at low strains, and then you reach some critical yield stress, and then the curve starts to turn over and flatten off towards some sort of steady state stress. And this is our elastic regime down here, and then we get into more of our plastic regime up here. So the theory here goes that if we apply just some small differential stress to the sample, and we can still be below the yield stress, right? So we've got a polycrystalline aggregate under some differential stress that's small compared to the yield stress. We take that aggregate across a phase transition, and so let's say this grain in the middle is going to turn into a different form, and it's going to increase its volume. So that volume increase is going to strain and stress the grains surrounding it. And so you'll get an internal stress that adds to the applied stress, and that nudges the system over this yield stress into the plastic portion of the curve. So that now if we unload this system along the same slope as our linear elastic modulus, we end up at zero stress with a permanent strain. And the theory here also predicts something about the way that the transformation is accommodated. So we've got two cases here that we'll look at. One is the hydrostatic case. So that's where we're not applying any sort of differential stress. We're just under a confining pressure. So there's no biasing in any way with the stress signal. We've got our three principal stresses, sigma 1, sigma 2, sigma 3, and they're all equal. So as we, in this case, get a volume decrease, we'll introduce, to accommodate that volume change, some defects here, some dislocations, and Elvira knows all about these. But those dislocations, because they're not being pushed preferentially in any particular direction, they're all just going to kind of glide around in random orientations. And so the phase change is going to be accommodated isotropically. We're just going to get equal amounts of shortening and contraction in three orthogonal directions. So now if we think about non-hydrostatic conditions, so in this case, we're going to be pushing more along the cylinder long axis than we are in the cross-sectional plane. In this case, we still introduce all these defects, but now they're being preferentially pushed in a particular direction. And so they're going to glide and move around cooperatively, and they're going to bias the volume change along that maximum principal stress direction. And so you'll get an anisotropy. It's the same amount of volume change, but you get an anisotropy in the volume change, which means that you're not shrinking in this direction. You're doing all of your volume change and all of your shape change along that maximum principal stress direction. So three key things to just bear in mind as we go through the talk. Phase transformations are thought to introduce transient weakening. So this is weakening just while you're going through the phase transformation. There are other things that will give so phase transformations can also give longer-lived weakening. We'll look at that really briefly. But in this case, in this talk, we're mostly interested in just the transient effect as you pass through a phase transition. You have a volume change that should be under differential stress conditions accommodated mostly along the compression axis. So we're looking for anisotropy in the way that the volume change is accommodated. And we're looking to see if strain is proportional to the applied stress. So if it follows this model of Greenman and Johnson. Now, all of these observations and this theory about transformation plasticity put together, this idea that we can transiently weaken as we go across phase boundaries, that's been invoked in a number of settings where we've got material inside Earth's interior being moved through pressure temperature space. So people have invoked transformation plasticity as being important for weakening across the mantle transition zone, so potentially playing a role in decoupling mantle convection, causing slabs to weaken as they pass through the transition zone. So you get this shallowing and stagnation of slabs in between the 410 and 660 discontinuity. So here are some topography results showing the Pacific plate going down into the mantle and China, I think, and then flattening out and stagnating in the transition zone. Similarly, material coming up through the mantle, you might get mantle plume necking or broadening as that material undergoes phase transformations. seismic uncoupling along subduction interfaces, deep focus seismicity, shear zone nucleation during mountain building. So a whole range of settings in which this might be important. And in fact, Jean-Paul Poirier, in a paper describing transformation plasticity in 1982, he said this, he writes this: indeed, one might well ask whether transformation plasticity could not be considered as the primary deformation mechanism in the crust, as well as in most of the upper mantle between 400 and 800 kilometers depth, which is pretty provocative. But it's good part of the proposals. So the talk really is going to touch on 3 topics. We're going to look at some mechanical data from pushing quartz across into the Quartz-Coesite phase transformation. So we'll see if we can identify transient anisotropic weakening during a phase transformation. We'll look at how those phase transformations are accommodated at the grain scale. And then finally, we'll think about whether or not we can identify the rocks that have been previously through a phase transformation, but there's none of that higher pressure phase left. We've completely transformed back. Can we still tell that those rocks have been through a phase transition? And I should point out that the kind of second half of the talk here is really going to be work mostly that's been done by Rheological, who's doing a postdoc with me at Woods Hole. All right, let's go on to this first topic. So yeah, so I mentioned that not many experiments have been done looking at phase transformations on crustal and mantle minerals. And part of the reason for this is it's actually really difficult to resolve this transient weakening using the typical tools that we use for squeezing rocks. So these are kind of the 2 workhorses of the rock deformation community. We've got a Griggs apparatus here on the left. These were designed by Dave Griggs back in the 1930s, I believe. He built 11 of these at UCLA. This is one, I think, at SUNY. This is number 4 of those original 11. Sample here is encased in a thick steel pressure vessel, and it's packed in with a bunch of solid material that when you push on it, it generates confining pressure. So it's really difficult to actually see. In fact, we can't really see what the sample is doing inside this pressure vessel during the experiment. We can only see what happens afterwards when we bring it out. And that's not really useful if we're trying to identify stuff that's only happening while we're doing a phase transition. And then the other mainstay workhorse apparatus is this Patterson apparatus designed by Merton Patterson, where again, our sample, this is a gas medium rig in this case. So it's a kind of like a pressure bomb. We're applying a confining pressure on our sample using pressurized gas. But again, to have pressurized gas in the lab, you need a pretty thick pressure vessel. So again, quite hard to see what's actually happening transiently during an experiment. So we've been turning to the D-dia. So this is a deformation dia apparatus, which is a kind of a see-through rig, where we take, we've got 3 orthogonal pairs of anvils in the press. And so there's a top ram up above here, and we apply a pressure behind the main ram. So it pushes all of these anvils together. That generates our confining pressure, but then we can independently move this vertical pair of anvils. And so we can generate high confining pressures up to maybe 10 GPa or so, but then we can independently deform and apply differential stress to our sample using these vertical anvils. And the reason I've said this is a see-through rig is because we're doing these experiments at the Advanced Photon Source Synchrotron. So we're firing X-rays through the narrow gap between these anvils, through the sample, which sits right here. And so we're able to resolve a bunch of things that we otherwise wouldn't have access to in just a regular lab. And here's Reli loading one of our samples into the rig earlier this week. Yeah, so we're doing these experiments at APS, Argonne National Lab, only an hour or so away from here. So the way this works is you've got a linear accelerator here in the center of this big ring. This is basically a big electron gun. So we're firing a beam of electrons into this booster synchrotron. This accelerates the electrons to about 99.999999% of the speed of light. So they're pretty rapid. And then they get released into what's called the storage ring. That's the ring that goes around in this main building. And the neat thing with electrons is when they change their trajectory, they emit X-rays. So you've got electrons moving around in a big circle here and emitting X-rays off at a tangent to the ring. And those X-rays, using a bunch of high-powered electromagnets, are channeled down 35 individual sectors. And each individual sector has 4 workstations on it. So you can have a lot of experiments going on at one time. We're over on, our experiments being conducted over on sector 6, which is somewhere around here. I think this might be sector 6. So what this means is we've got X-rays coming in through our passing through the gap in the anvils, through our sample, and then they're being detected downstream by 10 detectors arranged in an array like this. At each one of these detectors, we get an energy dispersive X-ray diffraction pattern, and the peaks in these patterns. So we've got different colors for and 10 different spectra for each detector. The peaks here correspond to specific crystal lattice planes in our aggregate. This is a pattern for olivine, the forthright. And the positions of these peaks tell us something about the lattice spacing, how closely those crystal planes are spaced apart through an experiment. And we can use this to calculate some sort of in situ stress. So let's just take, for example, detector. These are the 2 detectors really that we care about. We've got detector 1, which is detecting and it's measuring the vertical spacing between horizontal lattices. So that's this spacing right here. If we've got our ball and stick crystal lattice model. And we've got detector 5, so that's measuring our horizontal lattice spacing here. And when it's just a room pressure and temperature, those spectra should look identical. Lattice spacing should be nice and even if we're looking at the same crystal plane. If we apply confining pressure now to this, so we're pushing on the crystal in equal amounts in all directions, that crystal lattice, we can think of each bond as a spring. So those springs are going to push together, and we'll get a shift of these XRD patterns towards smaller lattice spacing. So we're decreasing lattice spacing as we apply confining pressure. And now if we apply a differential stress, so we're going to push more in the vertical direction, we'll see that detector 1, these peaks shift to even smaller lattice spacing. And so we can use the difference here in lattice spacing to give a strain on the crystal. And then from the elastic properties of the material, we can figure out stress. That's a fairly simple thing to do. So we get stress in situ. We can also get strain in situ. So in addition to the energy dispersive X-ray diffraction patterns, we also get X-ray radiographs. And so here we're looking at our deformation cell. This whole cell that is inside a cube is about 6 millimeters in each direction. In a typical experiment, we have anvils on the left-hand side that have sintered diamond tips. So those are X-ray transparent. And then on the right-hand side, we have tungsten carbide anvils, so they're opaque to X-rays. And then to be able to see where our samples are precisely, we encase them, we just put nickel foils around them. So those are dense and they absorb a lot of X-rays, so they appear as dark lines on a radiograph. This is just a sample of quartz being squeezed uniaxially, and we've got our olivine sample down below, which we use kind of as, ideally we want to use it as an elastic standard for getting out stresses, and we use this effectively as a stress sensor because the elastic properties for olivine are pretty well constrained as a function of pressure and temperature. And so we'll take each one of these radiograph images and do a digital image cross-correlation. And that gets us down to about a microstrain resolution. So we can resolve really small sub-pixel changes in sample length and strain. The other thing that we can do using the XRD data, and that's particularly important for these experiments, is we can calculate mineral phase proportions for an experiment. So each mineral will produce a distinct set of peaks in our X-ray diffraction spectra. So this is a spectrum for quartz with just as there are a bunch of other peaks out here, but I've just cropped it around this one main peak. And so I'm going to play a little movie that through time we're going to take this sample and push it up into the Coesite field. And so you'll see that this peak for quartz goes away and it's replaced by two peaks, one either side, that correspond to Coesite. So let's have a look at that. Here are these Coesite peaks coming in and the quartz one goes away. And we can use the relative heights of those peaks to calculate and say something about the volume proportions of those two minerals through time. So it's pretty neat. And some of Rheoli's experiments, we've been trying to capture and quench the samples right as they're going through the phase transition, which at some of these conditions will happen within about 5 minutes. So it's really crucial that we're able to really nail down where exactly we are in terms of volume proportions. Just as kind of we wanted to do just a test and see how reliable these measurements are. So this is one example spectrum where we've got a peak here corresponding to quartz and then two Coesite peaks. If you calculate the relative heights of the peaks, you end up you predict that we've got about 66% Coesite. And so what Rheoli's been doing with Veronique Leroux at Woods Hole is doing CT scans of the samples when they come out. And in the CT scans, you can see the darker material, denser material is the Coesite, which forms these big tabular lats, these big needly things. So we can look at volume proportions for the entire sample, or we can cut it down to what we call is the pencil, and this is the amount of material that's actually being sampled by our X-ray beam in the experiments. And so Rheoli's been working on quantifying volume proportions for a whole bunch of experiments where we've quenched midway through. These are what the CT scans look like. And we've actually got quite a bit of wiggle room in terms of where you actually pick the threshold for separating out those two phases. So this is kind of a lower bound, conservative lower bound, and then a conservative upper bound on the amount of Coesite. So Coesite is the orange phase here, and then quartz is in blue. And then this middle, kind of our middle happy medium estimate gives conveniently 66% Coesite, which perfectly matches our spectrum here. We also do have other constraints from EBSD data. So this is where we've taken the sample, we've cut it in half, polished it down, and then looked at it in an electron microscope. And in this case, for a particular section through this sample, we've calculated about 75% Coesite. So yeah, we're able to predict with this method volume proportions within probably 10% or so, which is pretty good. It's good enough for what we need. All right, let's look at some experiments. So we've got our phase diagram for SiO2, pressure versus temperature. We're going to take a sample of quartz, of hot pressed quartz. We're going to hold it in the alpha quartz field for some period of time. And then we're going to increase pressure under constant temperature. We're just going to increase pressure up into the Coesite stability field, hold it there for some period of time, and then bring it back down into the alpha quartz field. We've got two really main types of experiments. We've got these so-called hydrostatic experiments where we're not going to apply any differential stress to the sample. We're just going to increase pressure and then bring it back down. And then we've got our second set of experiments, which are these so-called non-hydrostatic ones, where we're actually applying a differential stress. So we're deforming the sample as it's going through the phase boundary. So here's our just one experiment, hydrostatic experiment, 900 degrees C for SiO2. You'll see that hydrostatics in inverted commas here The reason for that is the D die doesn't compress and decompress perfectly hydrostatically. We do get some wiggle in the amount of differential stress that's being felt by the sample. So it's on the order of tens or maybe up to 100 or so MPa through the experiment, but still relatively small. So when I play this movie, I'll probably play through it a couple of times. But what you're going to see is we'll just sit in the alpha quartz stability field for some time. We'll get a pressure ramp up into the Coesite stability field. We'll hold there, and then we'll bring pressure back down. You'll see the live radiograph images flicking through. So as a reference, I've drawn a red box around the starting dimension to show the starting dimensions of our quartz sample. And then we've also got our XRD spectrum. So you'll see this peak go away and be replaced by those two Coesite peaks that we were looking at before. And then we've got axial strain. So that's the amount of shortening in this direction of the sample. And we've also got volume strain. So one of the key things that we're doing with these experiments, I said that normally we'd have opaque handballs on the right-hand side because we only really care about measuring the shortening in the sample. In this case, we're swapping out our handballs for all four. We're using all four diamonds. So the whole sample is X-ray transparent. And we're able to measure not only changes in length, but changes in width. And from there, get changes in volume. We don't normally, the only reason really that we don't use four diamonds as routine is they're about $700 a pop. So if you break them, it can rack up quite quickly. All right, let's take a look at this. So we're ramping up through now. You'll see a change in the spectra. Differential stress, there's a little wiggle. The stress drops as we go through the phase transition. We got a big tick up in volume strain of about 10%. That's so some of that is just because we're increasing pressure, so we're pushing those atoms together. But then this big jump right here, that's the actual phase transition. So that gives us about 6 or 7% volume decrease, and we get about 3 or 4% axial strain just from the phase transition. And then going back down, we end up with, so our olivine load cell, which doesn't undergo a phase transition, that ends up back at the volume that it started at. But our quartz sample has lost some volume. So positive here means the sample has shrunk. This is, we figured out pretty early on, this was the first experiment we did, we figured out pretty early on that this permanent volume loss just corresponds to, there's some small amount of porosity in the sample to start with that packs down as we're increasing pressure. So that's why the sample is slightly smaller at the end of the experiment. Every experiment that we've done since this one, we've done kind of a pressure cycle at room temperature to begin with. So we're not transforming the sample, we're just packing all the grains together to get rid of that porosity. And then we end up back at a starting volume. Maybe I'll just play that through again. So you look, there's small amount of volume decrease in the SiO2 sample that you'll see. And then as we go through and start ramping back down, you'll see that the sample expands again. Here it goes. And it starts out exactly the same dimensions that it was at the beginning of the test. Although, yeah, I guess there is a small volume decrease that it's difficult to see on this. All right, let's look at our non-hydrostatic comparison experiment. So again, at 900C, it's basically the same PT path. We're just going to ramp up in pressure to Coesite and then ramp back down. But this time we're driving those vertical ramps in a constant, we're increasing the pressure behind them by driving syringe pumps in at a constant rate. So that kind of approximates a constant rate experiment. Yeah, and in this case, it's around 10 to the -5 in strain rate. So let's play through. We're now deforming and waiting to see if we get to some sort of steady state. The sample ends up straining at a steady state, but the stress is still going up. We start our pressure ramp here. We get a big drop in differential stress all the way down to 0 as we transform to Coesite. Then the sample hardens and strengthens up again to some sort of new stress state of around, yeah, stresses here are on the order of sort of a GPa, slightly more than a GPa. We're going to decrease to our pressure ramp down. And again, we're going to see the stress will drop. It's not going to go all the way back to zero. Instead, it's pretty much just going to go straight to steady state back in quartz. And the stress in quartz at the end is slightly lower than it was beforehand. Basically, that just corresponds with some grain size reduction that you get through the phase transition. The volume strain story is pretty straightforward. You get 10%-ish shortening from both the transformation itself and from the fact that you're just increasing pressure and pushing those atoms together, and then you recover your initial volume. But then in this case, the axial strain, so it increases kind of throughout the experiment just because we're pushing on the sample, we're deforming it. You get a tick up in the axial strain, so it shortens as it goes through the phase transformation as the volume is decreasing. But then on the way back down, the volume's increasing. So you might expect the sample to lengthen, but instead it shortens again. And what's really interesting here is as it goes through the phase transition, then the olivine load cell, which has pretty much just been going at a constant rate, then that starts deforming much quicker. So we think what's happening here is that the quartz is trying to expand this way, but it's pushing up and loading up the olivine sample stacked below it. And so the olivine starts to yield and deform a bit faster. The radiographs here are really spectacular. So we're just shortening at a constant rate. So you'll see this foil will start coming inwards. And then as we start our pressure ramp, once we go through the phase transition, you'll see extra little bit of shortening right here. So the sample's not really getting wider, it's only getting shorter. We're going to sit now in coesite and just form in coesite at some more or less steady state rate. And then as we go back down through pressure on our ramp back down, again, you'll see that the sample gets a lot shorter again. So it gets shorter and then it widens out as well. That's, yeah, quite neat. All right, let's look about what this means in terms of sample shape. So what we mean change in aspect ratio here is basically just the diameter of the sample divided, or the height of the sample divided by its diameter. So this value of 1 here means that if the sample were to maintain its shape throughout the whole experiment, it might get smaller, but then bigger. It would stay at a value of around 1 here. So under our quote-unquote hydrostatic conditions, you get a small increase in the aspect ratio here, and that corresponds with sample flattening. But then crucially, once we go back from coesite into quartz, we get sample lengthening. So it ends up being the same shape that it was to begin with. So I guess under our perfectly hydrostatic conditions, like the little cartoon model that I showed earlier, under hydrostatic conditions, we'd expect no real change or no anisotropy in the volume change. We're seeing a small amount of anisotropy, a small amount of flattening. Now, our non-hydrostatic case, on the other hand, we're getting constant flattening just again because we're squishing the sample, we're flattening it like that. As we go through the phase transition on the way up from Quartz-Coesite, we get small increase in flattening. But then really we get a big increase in the amount of flattening as we go back down through pressure. So the sample's getting bigger and it's expanding outwards this way. So we measure quite a lot of flattening, as you can see in the comparison of the radiograph with the initial dimensions. And so this is kind of our anisotropy that we're looking for. That's one indication that we've got transformation plasticity type things going on, as well as that 2 order of magnitude weakening that we saw in differential stress going through. This is a pretty busy slide. Each one of these plots is a plot of viscosity. That the y-axis is the same in each one, and then it's as a function of time in hours on the x-axis. So we've got, viscosity is just the stress at any given point divided by the strain rate. So the first derivative of strain. As we go from left to right, we've got slow. We're slowly deforming the sample here. We've got some medium strain right here, and then this is a relatively fast squishing. And then as we go from top to bottom, we've got, these are all cold experiments. So these are 700 degrees C and then 900 degrees C down here. Let's think about temperature first. If we compare the top row with the bottom row, the arrows here indicate where we're actually going through the phase transition. We'll see that, for example, slow deformation under cold conditions, we get maybe an order of magnitude, maybe 2 orders of magnitude, just transient weakening and a decrease in viscosity right here. But then the viscosity ends up being recovering back to its initial value, maybe slightly higher because Coesite slightly stronger. And then you get a little dip again as you go back through the phase transition. So we're seeing weakening here, but magnitude of that is more or less similar at cold and hot conditions. You can see that more with this middle column where the curves look quite similar really. The amount of transient weakening here is about the same magnitude. We don't really see too much of a viscosity, or we see the most dramatic viscosity drop is during the up pressure transformation. So that's going from quartz to Coesite. As we go back down through, we don't really see too much of a drop off in viscosity. And then once we go to our fast deformation rate, then we maybe see a tiny little blip, little decrease in viscosity. But really, there's not much of an effect there in terms of sample strength. And so what this shows is, well, it shows a couple of things really. It shows that phase transformations can produce 1 or 2 orders of magnitude transient weakening. That's we only see that as the sample is actively transforming, and then the strength recovers. So we do see the transient weakening, but it's mostly a slow, when we're slowly deforming the sample. And so it turns out, I think that when your rate of transformation is fast relative to the rate of deformation, then you see more of an effect. Whereas if you're deforming really fast and the transformation is relatively slow, then you see less of an effect. All right, so let's think about and look at what this actually looks like on a microscopic scale. And again, here we're moving more into this is mostly from here on what Rheoli's been working on for her postdoc project. A technique that we'll lean on quite heavily here is electron backscatter diffraction. So we've got a highly polished tilted sample in a scanning electron microscope. We're going to fire an electron beam at the sample. Those electrons are going to interact with a shallow, or with quite a small activation volume in the shallow near the surface of the sample, and they're going to diffract off in all sorts of directions, and they're going to diffract along crystal lattice planes to produce a series of cones like this. And those cones are going to interact and intersect a phosphor screen. This is our detector here. And as the electrons hit the phosphor screen, it'll luminesce. And we can capture that luminescence with a camera situated all the way back here. So this is just a reflector for one particular crystal plane, but we've got crystal planes in all sorts of directions. So we end up with a bunch of bright bands that we can then convert using a special algorithm. We can convert those into specific crystal lattice planes, and that's based on the crystal structure of a particular mineral. And what this means is we're able to resolve both crystal structure from the spacing and the angles between the bands that are unique to different minerals and different crystalline materials. We're also able to resolve orientation. So you might see a rotation of the pattern that corresponds to rotation of the crystal lattice. So we rest of the electron beam across the sample in a grid. Each analysis spot, we get a crystal structure. So we've got a blue cubic phase and an orange hexagonal phase here. And we're also able to resolve changes in orientation. So we can take this information, we can divide it up into regions of different phases. So orange versus blue and different orientations, build up things like phase maps and also orientation maps, where the colors here correspond to different crystal orientations. So these are phase maps for, on the left, we've got our quartz starting material. So we've just taken we took our quartz material up to pressure temperature conditions and then brought it back down just to see what it looks like right at the start of our experiment. We've got grain size on the order of a few microns, on up to 10 microns, let's say. Then we've got experiments where we quenched it halfway through the transition from quartz-coesite under hydrostatic conditions and then under non-hydrostatic conditions. So we see we've still got our blue polycrystalline quartz aggregate here with about the same grain size as starting material. And now we've got these big lats, these big tabular things, which are our coesite grains. And we can think about how those two phases are accommodating the phase transition by thinking about how internally bent and deformed those crystal lattices are. So what's being shown here is for a given grain, we calculate so a given grain in one of these maps is made up of a lot of pixels, a lot of analysis spots. So we can calculate the orientation, the angle between each pixel's orientation and the average of the grain. So if the coloring is blue, it means that within a particular grain, the lattices are completely uniform in orientation. When you get hotter colors, it means that there's some local bending of lattice. So for the most part, our undeformed starting material is fairly uniform orientations within individual grains, so it's not too beaten up. If we pluck out just the quartz grains from our EBSD maps, so we got a few small areas remaining. Again, we don't really see that much internal. I'm going to use the phrase misorientation, but that's what this is what it's referring to. It's just internal changes in orientation that indicate some sort of intragrain deformation. So in both the hydrostatic and the non-hydrostatic case, quartz isn't really doing an awful lot. It's just kind of sitting there. It's not being internally deformed, which we might expect. But if we look at the coesite now, this is our nucleating phase. We see warmer colors. So we've got these big lats of coesite, and those are actually quite beaten up inside, which we weren't expecting for a phase that's brand new and it's just forming. But we get all of these little subgrain boundaries, all the substructure that indicates that those crystals are being deformed. So thinking about the quartz, we wondered if maybe we just didn't have the amount of precision that we needed with EBSD. Regular, bog standard EBSD will get you precision in terms of orientation down to about 0.5 degree. So something that we've been playing around with, and this is really work in progress. There's not too much that we've got to show for this yet. We just spent a week in Cambridge with Dave Wallace, who's really an expert in this high angular resolution EBSD technique. So in this case, instead of just fitting a solution to our pattern and then throwing the pattern away, we're going to store all of the patterns for our maps, and we're going to pick a reference pattern for an individual grain. We're going to draw a bunch of regions of interest on that pattern, and then we're going to cross-correlate our reference pattern with the patterns, with all the other patterns in the grain for each region of interest. And so doing this, you can resolve things like rotations and also elastic strain. So it's kind of hard to see here, but the electron pattern here has been squished in a horizontal, along the horizontal axis. And this will get you about up to a 2 order of magnitude increase in angular precision. So you can resolve really tiny changes in crystal orientation that can then be used to resolve even smaller defect densities. And the 2 bits of information really that we're interested in here, and that we can pull out, we get the elastic strain, so that's just the squeezing and squishing of the pattern itself. This, if we know the elastic properties, the elastic constants of our material, we can get elastic stresses, we can get residual stresses from this information, and we also get rotations, which we can then use to build up a distortion tensor for our grains, and from there get out dislocation types and dislocation densities. We're still working on getting to that point, but what we can show are, here's just our regular old EBSD map. Again, this is one of those misorientation maps where the hot colors indicate more bending and the green orientations indicate regions of fairly uniform crystal orientation. We can take a first derivative of this to pick out the sites of, and again, this is just our conventional EBSD data, to pick out sites of crystal lattice bending. So anywhere where you've got linear features like this, that's a localized little wall where the crystal lattice is bent on either side. So with our conventional EBSD map, when we take this first derivative, we notice that it's really noisy, and we're not really able to see that much detail. So our noise floor here is about half a degree or so. If we do cross correlation, now we get an order of magnitude increase in precision. So we're able to pick out features a lot more cleanly. So you can see this subgrain wall in here quite nicely. You see another one that kind of runs up here. And down here through the corner of this grain, we've got a subgrain wall. So this corner of the grain is just bent away from the rest of it, a slight amount. Right, so here's that same map on the left. This is our quartz starting material. So we've got some internal deformation of the quartz starting material. It's not perfectly undeformed. We've got a few subgrain walls and defects in there, but not an awful lot. Now, if we look at the same type of map, one of these misorientation maps for our hydrostatic case, so we're not actively deforming the sample here, we're just taking it across the phase transition. We've got a big region of coesite in the top left here, and then a few quartz grains down here, in here, and in here. So the quartz in this case, if we just think about that, this is possibly even less deformed than it was to begin with. And all that comes from is the fact that this one was sat around under hydrostatic conditions for a bit longer at temperature, and so you've annealed out and you've gotten rid of some of the defects that were in the starting material. So the quartz is undeformed, but if we now look at the coesite, this is again where we're picking out all of our defects and all of our hot colors corresponding to local bending and deformation of the lattice. So the same thing holds up. It's not the quartz, it's not the original phase that's being replaced that's deforming, which is what a lot of the theory would suggest. It's actually, we're getting a lot of deformation in the new phase, the thing that's new phasing. So we're still trying to figure out what that all means and how that scales as a function of temperature and stress and strain rate, stuff like that. This is kind of just a little aside. Something curious that we noticed, although I noticed when putting this talk together, if you compare, so we've got one of these non-hydrostatic experiments at 900 C, we're driving the rams in at 0.003 millimeters per second, which is kind of our medium strain rate. We've got our quartz that then weakens, and then we're in the coesite field here. So our coesite stresses at 900 C are around 1 to 1.5 GPa. That fits pretty well with a flow law with other experiments that people have done on coesite. So that's good. Once we go to 800 C, so we're going colder now, the sample gets weaker, coesite gets weaker. And as we go, so our steady state-ish stress here has gone from about just over a GPa down to 700, 750 MPa. As we go to 700, again, same rate, but lower temperature. Now our steady state stress is 500. This is quite weird. If we think normally about crystal materials, we expect them to get weaker as they get hotter, as they get softer. But in this case, we've got material that's getting weaker as it's getting colder. And just to prove that we're not totally crazy here, I had our overnight shift. People on that overnight shift last night run an experiment where we just formed coesite and then we deformed it at a constant rate, but we did a series of temperature steps. So in this case, we're going down in temperature and we're getting strengthening. So this is what we expect to see, but we're seeing the opposite in the transformation experiments. So something about the phase transition is actually causing the sample to weaken as it goes to lower temperature. And we can again turn to the EBSD data to think about why that might be. So we've got a hydrostatic experiment. This time it's 700 C, and then hydrostatic at 900. So this is the sample. This is one of the maps we've already looked at. Again, blue is quartz, orange is coesite. So we've got a big tablets, tabular grains of coesite at 900 C. At 700 C, we see that the grains are much more needly. And particularly when you look at the orientation maps of these, you'll see that these are kind of splaying needles of coesite, much narrower and very long. Now, if we look at our misorientation map for these two samples, again, we've got a fair amount of crystal lattice bending at 900 C, but it looks really crazy when we go to 700 C. There's lots of internal deformation here, and these coesite needles that are nucleating are really being bent up, and they're accumulating a lot of defects. And so one of the things that the defects will do is they'll drive grain size reduction. And so the idea here is that maybe at lower temperatures, we're introducing more defects, so we're getting more grain size reduction after the transformation's finished. And so that is giving us the weakening that we see in those experiments. Yeah, not much more to say about that. We're going to do more experiments to kind of explore this the next time we come back to the beam. Kind of take one of these experiments and quench the sample here and here and here, and just see what the grain size and model microstructure looks like. See if we can correlate the strength and that kind of inverted weakening with changes in microstructure. How am I doing on time?
You're out of time.
I'm out of time.
Well, no, if you want to finish in a minute, then we'll try to take a couple of questions. But
Yeah. All right. So, can we identify quartz that's come back from coesite? A lot of this comes from metamorphic petrology, where we'll get there are cases where you get tiny bits of coesite preserved within quite strong phases. So this is quartz that's overprinting coesite. You get these big needles. And again, there's another example. You get needles of quartz growing out from some sort of medial line that was formerly a grain boundary in coesite, people think. If you take one of these samples where we've got a big coesite grain and you look at the quartz around it, you notice if we just look at C-axis orientations, we've got distinct clusters, even though we've got hundreds of grains here. So we can look at two particular clusters here that seem to be oriented, they're misoriented, so they're about 90 degrees away from each other. We can break those out into different subsets. So we've got our C-axis grains with our C-axis cluster here, and grains with our C-axis cluster here. And if we look at those, they're misoriented, yeah, like I said, about 90 degrees away from each other around this axis up here. That's the rotation axis that fits through those 2 points. And that corresponds to a shared A-axis in the quartz. So there's a particular crystallographic signature here that people have found in natural rocks. We wanted to see if we could find that in our experimental rocks. So what we did is take a quartz single crystal, we transformed it to coesite and quenched it. That's kind of our starting reference material in this case. And then we did another experiment where we transformed it to coesite and then brought it back to quartz. And so you can see after the experiment, we've taken a single crystal and turned it into about 10,000 grains. So we've got a lot of grain size reduction. And we've got a few distinct peaks in our C-axis pole figure. So our C-axes or our orientations tend to cluster into 4 broad groups. So we can separate out those 4 broad groups here. Each one of those groups, even though it's made up of hundreds of grains, has an apparently single orientation. So if we look at the pole of rotation between these clusters, for orientation groups 1 and 3 that are next to each other, orientation groups 2 and 4 that are next to each other, they're rotated again by about 90 degrees around a common A-axis. So the same relationship holds up. And I'll leave it there. So we can get transient weakening. We also see long-lived weakening. Internal stresses are highest in the nucleating phase, and we can use quartz crystal orientations to tell whether something's been to ultra high pressure conditions. And then finally, some science gone wrong in the theme. And in keeping with the Halloween theme, Elvira tipped me off. So we've got, this is an experiment just from earlier in the week. We were trying to heat this and anneal a coesite single crystal, but we inadvertently melted our nickel jacket. And so you've got these blebs of nickel coming away. And then we've got a cracked tungsten carbide anvil. I don't even know what happened here, but we somehow shattered a sintered diamond anvil. This was quite spectacular. And then finally, great. Just again, shout out to a great group of collaborators on this. Thank you. Sorry for that.
So much, Andy. We did run out of time.